In this video, we're going to be discussing section 4.6 out of the OpenStax Calculus book, volume 1. This section deals with graphing functions. Earlier this semester, we dealt with the first half of this section when we looked at limits at infinity and infinite limits. We're going to focus on the last few pages of this section, beginning on page 425 with the guidelines for drawing the graph of a function. You'll see a copy of the gold box here on OneNote, and let's go through what these various steps are. The first thing we need to do in order to graph a function is to determine what the domain of the function is. There are several reasons for this. Restrictions on the domain can provide information about where there are holes in a graph, where there are vertical asymptotes, and also what values, critical values, can be used for places where we have relative extrema and for inflection points. If a value is not in the domain, it cannot be a critical value, which means it cannot possibly be the location of a relative extrema, nor can it be an inflection point. If it's not in the domain of the function, then the graph does not exist at that point. So the first thing we will always determine is the domain. When looking at the domain, there are two primary things we look for: no zero in the denominator of a fraction and no negative under an even radical. These are the two primary ways that we can have a restriction on the domain. However, they are not the only ones. For example, natural log carries its own natural restriction on the domain. The domain of natural log's argument must be open 0 to positive infinity. That's not the restriction on x, that's the restriction on the entire argument to the natural log, which may be x, but may be some expression containing x. After we have determined the domain and know what values got thrown out of the domain, then we will look for the X and Y intercepts. These are the basic points where the graph crosses the x-axis and the y-axis. You've been looking for these points probably since middle school. The third thing we will be looking for are the limits as the function as x goes to infinity and the limit on the function as x goes to negative infinity. Remember that when we first studied this, we called these end behavior. This is where I say you can play the Bill Gates rule, and the only place where you can play the Bill Gates rule. In other words, when the numbers get massively large in magnitude, the only thing that matters is the highest degree term in the numerator and the highest degree term in the denominator. If the degree of the denominator is larger than the degree of the numerator, it will overpower it and eventually drive the horizontal asymptote down to 0 or to the x-axis, which is the same thing, the graph of the line y equals 0. If, on the other hand, the degree of the denominator is equal to the degree of the numerator, then they have equal magnitudes of infinity, and neither will win out. In this case, the horizontal asymptote for a rational function will be the ratio of the leading coefficients. That is, the ratio of the coefficient of the highest degree term in the numerator divided by the coefficient of the highest degree term in the denominator. This is when the degree of the numerator and the degree of the denominator are equal. On the other hand, the last possibility is what happens when the degree of the numerator is larger than the degree of the denominator. I call these kinds of functions top-heavy because in the sense they're like a fraction that is improper, where the numerator is larger than the denominator. When the degree of the numerator is larger than the degree of the denominator by precisely 1, there is a slanted line called an oblique asymptote that the graph of the rational function will approach as x approaches positive infinity and negative infinity. If it is more than 1 degree larger, then there will be an asymptote. It just won't be a slanted line. We will not be looking at too many of those. The next thing that we tend to look for after we look for end behavior is whether or not the graph has any vertical asymptotes. In fact, after you've examined step 1, which is the domain of the function, you will already know whether or not you have vertical asymptotes. You should also add to this step whether or not you have any holes. I would definitely add that into my list of things that I'm looking for at this point. So in addition to vertical asymptotes, make sure that you look for holes. Remember that holes occur when you have a factor in the numerator and a factor in the denominator that are exactly the same, but the factor in the denominator cancels and disappears from the denominator. Even if it is still in the numerator, it will be a hole in the graph occurring at that x-coordinate. To find the y value of the hole, plug that x-coordinate into the reduced fraction. That will give you the y value of the hole. The next two steps are the two steps we just learned in the previous section with the first derivative test and the second derivative test. We will find the first derivative and locate all the critical points where the first derivative is equal to 0 or where the first derivative is undefined, but the function is defined. By examining the first derivative, we can predict where the function will be increasing or going uphill and where the function is decreasing or going downhill. We can also determine with the first derivative where and whether the function has any local extrema. The second derivative can also be used to find local extrema using the second derivative test. However, the second derivative test does not work if when you plug in the critical point to the second derivative, you get 0. In that case, you have to go back and use the first derivative anyway. On the other hand, the second derivative gives us information that the first derivative cannot. It tells us which way the curve is bending over particular intervals. We divide up the domain of the function using the inflection points, which are the zeros of the second derivative, where the second derivative changes its sign from positive to negative or negative to positive. When you look at the graph then, you can tell where it is concave up or bent up like a cup shape that would hold water, sort of like a contact lens upside down. Or where the function is concave down, which means that your lens is turned over and nothing can get inside of it. It won't hold any liquid at all. It's turned upside down. That is called concave down, and we often say concave down like a frown to help you remember which way it goes. Once we have all these pieces of information, we'll sketch our best guess of what the function looks like. Let's get started on our first example. Our first example is the function 2x to the 6th minus 3x to the 4th. First, note that the degree of this function is 6. It is a polynomial, which means that both of the end behavior, both arms on the far left and far right, either both go up or both go down. Because the leading coefficient, the 2, is positive, they'll both go up. We have a couple possibilities that you should remember from earlier in the semester or from what you did in your college algebra. It's not clear what it will do in the middle, but at least on the ends, we know the end behavior should be it goes up towards infinity. Options are that it can come and wiggle in between and then go up again, or it could just come and flatten out, although never getting truly horizontal and going up again. Let's see if we can determine where these things happen and what the actual picture looks like. First, again, note that we deal with the domain first. The domain is going to be all reals, and the reason is it's a polynomial function. Once I know that, I know there's nothing I have to throw out. Now let's look at step 2. When we were looking at step 2 on the gold chart, we were trying to find out where the X and Y intercepts were. So now I'm going to find the X and Y intercepts. Remember that your X-intercepts from your college algebra class occur when Y is 0. I like to think of this as sort of like a football game. You throw an interception in football when the opposite team gets the ball. In this case, we think of 0 being the ball, so the X-interception is when the Y team grabs the ball away. That means that we're looking for ordered pairs with some value for the X coordinate, but 0 for the Y. In that case, we're going to replace the f of x with 0 and factor what we have left, 2x to the 6th minus 3x to the 4th. I have a common factor of x to the 4th, which I can take out, and that leaves behind 2x squared minus 3. This gives me several possibilities. First, if x to the 4th is 0, then I know that x could be 0. That means that one of my x-intercepts must be the origin. This is a really important point to note if you get it for an x or y-intercept, because this one, if you receive it, has to be both an x-intercept and a y-intercept. It's the only point that's on both axes at the same time. Because this is a function, and you know that because I use function notation, you know that it can have at most one y-intercept, because if it had more than one, it would flunk the vertical line test. That means that you have now the only y-intercept, which has to be the origin as well. Now I need to take the other factor, the binomial 2x squared minus 3, and set it equal to 0. Use the square root property to solve for x. Isolating the x squared gives me x squared equals 3/2. Taking the square root of both sides, I don't know anything about x, whether it's on the right or the left of the origin. This means x could be positive or negative, which means that x could be plus or minus the square root of 3/2. It is okay with me if you want to leave it as the square root of 3/2, but you can also rationalize it if you want by multiplying by square root of 2 over square root of 2. This would lead to the square root of 6 divided by 2. Just make sure that you do not try to reduce the 6 over 2. The 6 is under a radical, which means it's not really 6 at all. The 2 is outside the radical, which means it really is a 2. This gives me 2 additional x-intercepts. This gives me the square root of 3/2, or square root of 6 over 2, comma 0, and negative the square root of 3/2, or square root of 6 over 2, comma 0. That tells me I have 3 places on the graph where I am crossing the x-axis. I already have my y-intercept, but just for completeness, let's go ahead and talk about how to find the y-intercept. Just like in football, a y-intercept occurs when the y team throws an interception and the x team gets the ball. That means the x coordinate of the ordered pair is 0, and we need to find the y. This is why the origin, or 0, 0, has to be both the x and the y-intercept simultaneously. On a function, you can never have more than one y-intercept, but it is not required that you have a y-intercept. However, you can have many x-intercepts. In fact, the sine function and the cosine function have infinitely many x-intercepts. It is also possible that you have no x-intercepts on a function. This can also happen. Now let's continue with our search of how to figure out the information to graph our function. We need to talk about end behavior. End behavior we have already dealt with because we noticed from the beginning it was a polynomial of degree 6. However, for completeness, let's go ahead and write that down. It's a polynomial, it is even degree since it's 6, and the leading coefficient, or LC, is positive. That means it's going to go up to infinity as x goes to negative infinity, and it's going to go up to positive infinity as x goes to positive infinity. The far left and the far right of the graph go up to infinity. Now, what is our next thing that we need to consider when we're going to try to figure out what the graph looks like? The next thing to consider is whether or not we have any vertical asymptotes or holes. When I'm writing these down, I tend to abbreviate vertical asymptotes as VAs, and for holes, I actually do write it out, holes. In this case, we have neither vertical asymptotes nor holes. Remember what our original function is. It is f of x equal 2x to the 6th minus 3x to the 4th. There's no fraction, so there's no way to get 0 in the denominator, and there's no radical, so there's no way to have a negative underneath an even radical. That means I cannot have any vertical asymptotes or holes in the graph. The next thing I look at are the pieces of information we learned from the last section in section 4.5. Looking at step 5, I need to find the critical values. To find the critical values, I need to take the first derivative. In order to do that, let's copy our function and move it down here. I've copied our function, f of x equals 2x to the 6th minus 3x to the 4th. Now I'm going to take this and find the first derivative. The first derivative, by applying the power rule, gives me 12x to the 5th minus 12x to the 3rd. In order to know where the critical values are, we look at two pieces. One, the first derivative equals 0, and two, the first derivative does not exist, but the function f of x does exist. Since our function is defined for all reals, we'll look to see, are there any places where the first derivative does not exist? Looking at the first derivative, I can see that it's also a polynomial, so it must be defined everywhere. I will have no critical values coming from the first derivative not existing, but the function existing. Now I want to look at the second case. Where is the first derivative equal to 0? To do that, I want to go ahead and complete factoring of the first derivative. I have a common factor of 12 and a common factor of x cubed out of each term. When I factor out the 12x cubed, it leaves behind x squared minus 1. I can further factor x squared minus 1. Be careful that you do not stop factoring until every single factor group cannot be factored anymore. At this point, I can do nothing more. 12x cubed is a monomial factor, x minus 1 is a binomial factor that doesn't factor more, and x plus 1 is a binomial factor that does not factor more. Now I need to decide where's the first derivative equal to 0. Since I have three factors, I have the monomial factor 12x cubed equal to 0, and I have the binomial group x minus 1 equals 0, and the other binomial group of x plus 1. Setting each of them equal to 0 should give me the places where I will find critical values. If 12x cubed is 0, then x could be 0. That is one critical value. Solving x minus 1 equals 0, I get x equal 1 for the second critical value. Solving x plus 1 equals 0, I get x equal negative 1 for the third critical value. This gives me three critical values that I'm going to use to divide up the domain of the original function. Remember that the original function, since it's a polynomial, has domain of all reals. Then I look at my three critical values and I determine which one on the number line is furthest to the left. My furthest to the left is x minus 1. I'm going to write down the three factors that I have so far, and I'm going to create a number line for each one. 12x cubed is my first factor from the first derivative, and it consists of the monomial group 12x cubed. The second factor from x prime or f prime rather, is x minus 1. The third factor is x plus 1. When I multiply all three together, I get the combination, or what I can also call f prime. Drawing one number line for each factor and an additional number line for f prime, I'm ready to put the critical values onto those number lines as vertical lines. The one furthest to the left we decided was -1. We'll make a long vertical bar and label it -1. Another long vertical bar, and we will put the next one on the number line order, which would be x equals 0. We may need to extend our lines out to make sure that we have plenty of space and aren't running out. The last critical point, x equals 1, becomes the third vertical bar. Now I choose a test point for each of these values. A test point is a number that is not on a boundary line, not on one of the critical values, but does lie within each of the intervals of the domain split up by the critical values. For a number below -1, I'm going to use the test point -2. I like to circle mine so I can find them more easily. For a test point between -1 and 0, I will use -1/2. While there are infinitely many numbers to use, it's a good idea to use the easiest one you can think of. Between 0 and 1, I again will choose an easy number, in this case 1/2. For an easy number that's greater than 1, the easiest one I can think of is 2. Now I'm going to plug these test values into the different factors and determine whether they are positive or negative at that test value. Because the derivative can only change sign at critical points, or only at -1, 0, and 1, but is not required to change sign there, we know that within each of these regions, it has to maintain only one sign. If I take a -2 and cube it, I still have a negative. Multiplied by a positive is still going to be negative. Likewise, a -1/2 cubed is still negative, times a positive is still negative. When I cube 1/2, I get a positive value, times a positive is positive. Note that the solution that matches the factor 12x cubed is x equals 0, and that it does change sign precisely there. When I plug in 2, likewise, I also get a positive. We'll repeat the process for each of the two remaining factors, plugging in -2 into x minus 1 to get a negative, -1/2 minus 1 to get a negative, 1/2 minus 1 gives a negative, but 2 minus 1 is positive. And again, note that x minus 1 changes at its solution, or x-intercept, which was the critical value 1. For x plus 1, it should be changing at the vertical line for x equal -1, that critical value. Plugging in -2, we get a negative. Plugging in -1/2, we get a positive. There we see the sign change. The other values plugged in also give me positives. These three factors are multiplied together to give me f prime, the first derivative. When I multiply three negatives, it stays negative. Two negatives and a positive give a positive. Two positives and a negative are negative, and three positives are positive. Let's remind ourselves of what this means. When the first derivative is negative, it means it is decreasing or going down. That means in these two regions, it is going downhill. When the first derivative is positive, the function is increasing or generally going uphill. This means that I can take this information and write it down over here to the side and keep track of it. This tells me that it will be increasing over the following intervals. It should be increasing between -1 and 0, and again from 1 to infinity. The function should be decreasing or going generally downhill from -infinity up to -1, and again between 0 and 1. Note that this order matches the number line order, where negative infinity is to the far left and positive infinity is to the far right. The first derivative test can now be used to determine if there are any relative extrema here. There are some relative extrema here. We must have, in general, a minimum at -1 because it was going downhill, then it curves to go up. That means that we must have a relative minimum occurring at x equal -1. We'll find the y value for that in just a moment. Let's go ahead and identify any other extrema locations before we find the actual extrema values. What about at 0, the next critical point? It's going uphill and then downhill. That means we must have a relative maximum up here at the x value, x equals 0. The last one, going downhill as we approach 1 from the left and then uphill as we leave 1 to the right, means that we again have a relative minimum at x equal 1. Now, how can we find the values of those relative extrema? For that, we need to again find the actual function value. Let's copy it again and move it down so we can see it at the same time. I have reproduced the function down here for you to see. I've boxed it in red so that you can locate it. In order to find the actual relative minimum value, we need to compute the function, not the derivative, but the actual function at the critical point -1. When I plug that in, I get 2 times -1 to the 6th minus 3 times -1 to the 4th. A negative to an even power is a +1, so this leads to 2 minus 3, which gives me -1. That means my relative minimum value is -1 located at -1, or the ordered pair -1, -1. What about the relative maximum we found at 0? If you're remembering, then way earlier up here in step 2, we found that 0, 0 was both an x-intercept and a y-intercept. The fact that it is a function tells us that it cannot have more than one y value there, which means that this relative maximum must be that point 0, 0. If you're not sure, you can always plug 0 into the original function, and you will again get the same spot, 0, 0. What about the last point? We have another relative minimum at x equal 1. However, if we think about the relationship between the different terms of the function and the fact that x only has even powers on it, we know that whether we plug in -1 or 1, we will get the same value. In other words, f of x is a symmetric graph. It is symmetric with respect to the y-axis. The y-axis symmetry occurs whenever you have the function with x plugged in equal to the function with -x plugged in. If it doesn't matter whether the value you plug in is positive or negative and you get the same thing, then you must have y-axis symmetry. We can also have origin symmetry. Origin symmetry is what you will find on a sine graph or a cubic function. For origin symmetry, if you plug a negative value into the function, you do not get the original function f of x, but you do get the opposite of it. In other words, f of -x is negative f of x. This tells us that it has origin symmetry. There is such a thing as x-axis symmetry, of course, but it's not possible to get it here. Can you think about why we can't possibly have x-axis symmetry? If you're thinking about it, try to visualize what x-axis symmetry would look like. It would look something like that. What's the problem with that graph? You're right, that graph does not pass the vertical line test. It's not a function, and I used function notation. So the reason we don't get x-axis symmetry is because I started with a function. Most of ours will start with functions, but in Calculus 2, you should expect to see some curves that are not functions to start with. In that case, you might want to check for x-axis symmetry as well. Now, let's take a look at the next step. We need to find where our relative minimum is, and I said it must be y-axis symmetric. That means I should get the same y value out when I plug in 1. And in fact, if you check it, you'll find that you do also get -1. That means that it is symmetric across the y-axis. I have both -1, -1, and 1, -1 on the graph. At this point, we've gathered all the information that we can from the first derivative. Now we need to take a look at the second derivative to determine where it is concave up and where it is concave down. We can have a curve that is increasing, that is concave up, and we can have a curve that is increasing, that is concave down. They look fundamentally different. So learning about concavity gives us a much better idea of what the curve is actually doing. Let's compute the second derivative. I've reproduced the first derivative here just so it will be easier for us to find. Finding the second derivative, I can get, as long as I can get my pencil to come on, I get f double prime is equal to 5 times 12 or 60 x to the 4th using the power rule. 3 times 12 is -36 x squared, reducing the power by 1. Again, to find the inflection points, I want to look to see where the second derivative changes sign. To know where it changes sign, it helps to know where it's 0 or where it's undefined. In this case, I need to look to see where it's 0, since this is also a polynomial and is defined everywhere. That means I need to factor it by taking out any greatest common factor. I know that 36 will not come out of 60, but I know that both 60 and 36 are divisible by 6. I'll start with 6 and see if that's big enough. I know I can take out at least x squared as well. That will leave behind 10x squared minus 6. However, notice that 10 and 6 are still both divisible by 2. That means I could have taken 12 out of the original, and I should have. I can still take it out here at this point. Just keep in mind that when you're factoring out this, all the factors on the outside are multiplied. Taking out the common factor of 2 just gives me the 2 on outside, which will lead to the 12x squared I could have taken out from the beginning. Taking out the 2 leaves behind 5x squared minus 3. In fully factored form, then I have 12x squared times the binomial factor 5x squared minus 3. It looks to me as though the second derivative has 3 possible zeros with repetition. The second derivative is a 4th degree polynomial, so there should be 4 total solutions from the fundamental theorem of algebra. I hope you remember that from college algebra or pre-calculus. Again, they're coming from setting each factor equal to 0 and solving. If I set 12x squared equal to 0, I get x as a solution, x equals 0 as a solution, but because the power was 2, I get it 2 times. That counts as 2 of the 4 solutions for the 4th degree polynomial. Now I can take the binomial factor, 5x squared minus 3, and set it equal to 0. Since I have no x term, I can isolate x squared and use the square root property. This would give me 3/5. Taking the square root of both sides, since I don't know anything about x, leads to the square root of 3/5. Again, if your professor wants you to rationalize, you can multiply by root 5 over root 5, which is just a form of the number 1. that would lead to plus or minus the square root of 15 divided by 5. For my students, I do not care if you leave it as the square root of 3/5. Just be sure that that square root extends all the way from the bottom of the 5 to above the 3. This gives us our last two of the 4 solutions for that 4th degree second derivative. Now I'm going to take the domain of the original function and I'm going to split it up according to those values. This means that I can look at the 12x squared as one of the factors. And let me change colors so that we can see it a little more easily. The 12x squared as a factor and the 5x squared minus 3. Now, if I only use 5x squared minus 3, I am going to lose some information. I need to think about splitting it at these critical points, but I can leave the factor together if I want to. These two multiplied together do give me the second derivative, but notice that I got 2 solutions out of the quadratic factor, and that means I will have to have 2 vertical lines for that one factor. Drawing a number line for each of the factors and one for the second derivative, I now need to figure out which of the 3 unique values for where the zeros of the second derivative are is furthest to the left. It's going to be the negative square root of 3/5. Somewhere way over here, I have the negative square root of 3/5 or the negative square root of 15 divided by 5. In between, I have 0. And at the far right, I have the positive square root of 3/5. Now, in order to figure out a test point, we need to kind of know about how big the square root of 3/5 is. This is a good time to grab a calculator. I typically use a simple scientific calculator and find out how much the square root of 3 divided by 5 is in terms of decimals. It is roughly 0.775. That means this one on the left is roughly negative 0.775. A good test point then to the left of that would be -1. I can put -1 up here as my test point. Between -0.775 and 0, I would use -0.5 or -1/2. You can write it in either format. Between 0 and 0.775, I'll use 1/2, and above that, I will use the test point 1. Make sure when you're doing these that if there were restrictions on the original function's domain, that you do not accidentally choose one of those values as a test point. You cannot use a test point that is not in the domain of the function. In our case, the domain of the original function was all reals, so we're safe. Now let's plug in and figure out what our signs are. In this case, when I plug in, a negative squared is going to be positive. In fact, if I think about it, no matter what I put in for x, when I square it, it becomes positive, and times a positive 12 is positive. That means that entire first row is positive in all cases except when it's 0. What about the 5x squared minus 3? Let's plug in the -1. Squaring it gives us +1 times 5 is 5. 5 minus 3, that's positive. If I were to plug in the 1 on the right, I'd get the same thing since -1 squared and 1 squared are both 1. That means that this one is also positive. Note that I will have a similar relationship between the sign of 5x squared minus 3 at -1/2 and at +1/2. You may want the calculator to help you a little bit on this one as well. 1/2 squared is 1/4. 5 times 1/4 is 5/4 or 1.25. 1.25 minus 3 is definitely negative. That means both of those are negative. Since these factors are multiplied together to give me the second derivative, I can multiply their signs to find the sign of the second derivative. Remember, the second derivative tells us which way the curve is bending. It's concavity. Since this is positive, that tells me it's concave up like a cup when it is positive. Where the second derivative is negative, it is concave down like a frown. In this case, an inflection point can only occur at a place where we have a change in curvature. That is, when it goes from positive to negative or negative to positive. Where do you think the inflection points on this graph occur? You're right. The inflection points will have to occur here at this value and here at this value. Note that 0 cannot possibly be an inflection point because it stays concave down on both sides of that. That tells me that only at negative square root of 3/5 and positive square root of 3/5 do I have an inflection point. Let's write down the information we found in the bottom two rows of our chart now. I've discovered that it is concave up over the following intervals between negative infinity up to negative the square root of 3/5, which is about negative 0.775, and again between the square root of 3/5, or about 0.775, to infinity. I also know it is going to be concave down or turned down like a frown between negative the square root of 3/5 and the square root of 3/5. It does not change curvature over that region. The inflection points can only occur where sign change occurs in the second derivative. That means that I have two inflection points. My inflection points then must be the following. One is at negative the square root of 3/5 and some y value, and the other has to be at positive the square root of 3/5 and some y value. How am I going to find the y value of the inflection points? What should I plug those x coordinates into to find the y value on the true graph? You're right, not the first derivative, not the second derivative, but the function itself. Let's copy the function and move it down so we can see it all at one time. Now we have the function. We can plug the two x coordinates of the inflection points into our function. Note that because the powers on the variable x are both even, it won't matter whether we plug in the negative root or the positive root. If one of these powers were odd, I could not be plugging them in at the same time, as one with an even power will end up positive and any to an odd power will end up negative. If I were to take this value and multiply it by itself 6 times, that means that I would have to have 6 in a row of this 3 square root of 5. Every pair of those will give me 1 3/5. That's 4, 5, and that's 6. Each pair is going to give me 1 that counts as a 3/5. That means I end up with 3/5 times itself 3 times, or 3/5 quantity cubed. This leads me to 27 over 125. That is what I'd get for x to the 6th. Now I need to multiply it by 2. Multiplying by 2 would lead to 54 divided by 125. What would I get for the second part? Well, first, if I were to take the x to the 4th, I would have 4 of them. That would be 2 3/5 multiplied together, which would give me 9 over 25. Multiplying by -3, this would give me minus 27 divided by 25. Those are not like fractions. To find the like fraction, I need to multiply the second one by 5 over 5. That would give me 54 over 125 minus 27 times 5, which would come out to be 135. This would give me negative 135 over 125, and the final value then would come out to be 81, negative 81 over 125. That is the location of my inflection points, negative 81 divided by 125. To know about where it's going to be on the graph, you may want to use the calculator to get a decimal approximation. This value is roughly equal to negative 0.65. This one over here is also going to give me the same exact value, negative 81 over 125, also about negative 0.65. Now that we've gathered all these many pieces of information, and it's about 45 minutes later, let's figure out how we can put it together to try to draw the graph. Starting way back up at the top, what did we find out? First, the domain is everything. That means there should be no holes and no vertical asymptotes in my graph. Second, my x-intercepts are at 0, 0, square root of 3 halves 0, and negative square root of 3 halves 0. At this point, you should probably find out about how much the square root of 3 halves is. Using a calculator, I get that this is approximately 1.2. Let's go to our graph and just put on those 3 points, 1.20, negative 1.20, and 0, 0. Scrolling down, you'll see I have a graph prepared here. I'm going to try to choose a brighter color that maybe will show up a little bit better. Our points were 0, 0, which is here, 1.20, which is going to be just past the 1 mark, and negative 1.20. That accounts for our 3 x-intercepts, one of which is also the y-intercept. What else did we have? Let's scroll back up and see what other information we got. We know it's a polynomial, it's even degree, the leading coefficient's positive, so the end behavior should go up forever. We found no vertical asymptotes and holes. When we looked at our critical values, we learned that we had 3 extrema. One relative minimum at the value -1, -1, and another relative minimum at 1, -1. And 0, 0 was a relative max. Let's put those onto the graph and label them with min and max so we can remember what they're supposed to be. Again, the points are -1, -1, 0, 0, and 1, -1. Scrolling back down to the graph, 0, 0 was supposed to be a max. Maybe I'll just write it over here to the side. 0, 0 is a max, -1, -1, and 1, -1. These are both relative minimums. Where is -1, -1? That would be here. And 1, -1 is here. You can see that those so far do form a y-axis symmetric graph. Now let's see what other piece of information we have to add. I knew from the first derivative that it must be decreasing between negative infinity up to -1, and again from 0 to 1. Let's focus on the far left and get that piece in. Negative infinity to -1, it's decreasing. Is it concave up or is it concave down there? Let's look at the second derivative. The second derivative says that until about -0.775, it's concave up. I know that the ends have to be going up to infinity. That means I need to draw it in such a way that it is sort of curving up like a cup until it gets down to here. Now, once I get to there, what happens? Let's scroll back up to the first derivative chart and see what changed. At -1, it begins to increase until it gets to 0, and at 0, it begins to decrease again to 1. What about the curvature between -1 and 0 and 0 and 1? The curvature of this graph is going to change at 0.775. Where is 0.775? That's at about -0.8 and at 0.8. Let's go put those points on our graph. We found the inflection points to be at about 0.8 and, where'd it go? -81/125, which is about -0.65. Okay, that is not such an easy point to graph. So let's make a note of that here, that our inflection points are going to be roughly at the following locations: -0.8 or 0.775, comma, and -0.65, which is about -0.7. We probably can't get any closer than that. The other one is at about +0.8, but also at -0.7. Let's verify that that was what the two inflection points were. Yes, both y values are about -0.7. The x values are same in magnitude, but opposite in sign. Now I'm going to take and I'm going to put those on here with a slightly different color, and I'm going to make an X for the inflection points. Let's make the graph a little bit larger to make it easier to do. At -0.8, I go 0.8 of the way across to -1 and drop down to about 0.7. Right there, I need to change my curvature. On the opposite side, I have the same point. It's going to stay concave up until I get to that point, and then it's going to change. Concave up, and then it bends and it goes concave down. When it curves down, it stays down until it gets to the next inflection point, and then it bends to go up again. What about after that, between 1 out to our next x-intercept and beyond that? Scrolling back up and looking at the chart for the first derivative, I can see that from 1 to infinity, it continues to increase forever. Now looking at the second derivative, I know that from that inflection point, it is going to stay concave up. So on the graph, I need to draw something, and let me blow it up again so that you can see it a little bit better, so that it is curved with a bend up, but going up to infinity on both sides. This is roughly what the graph needs to look like. Now let's take a look at something on Desmos to see how close we got with our estimate of what the graph looked like. I'm going to scroll back in and I'll produce and copy the graph from Desmos directly below. Let's see how we did. This is a graph of our function on Desmos. You can see that I've plotted the two inflection points as X marks, and you can see our approximations are the same as what we got. You'll notice that this does appear to be curved up like a cup until it gets to that inflection point where it changes to a downward curve like a frown. And then again, it changes at this inflection point and is curved up. Our hand-drawn graph is remarkably close to the one produced by Desmos. If you look at ours up above, you can see that they are very similar. Although granted, Desmos has a much smoother hand than I do. I'm going to give you another problem that I want you to try on your own. I want you to pause the video after I give you the function, and I want you to go through all of the steps, finding each of the pieces, and try to produce the graph on your own. When you think you have it all ready, Turn the video back on and compare your answer to the one I got. Now let me give you the function to try. The next function to try is the function 2x times the square root of 16 minus x squared. You'll need to be careful on this one because it definitely has a restricted domain. Notice that if x is any number whose magnitude is larger than 4, you'll get a negative underneath the square root, which is not allowed for real numbers. That means that your domain will need to be between -4 and 4. Pause the video now and run through the 6 steps of finding all the information out that you can about this function and try to produce a hand-drawn sketch of what it looks like. When you're done, turn the video back on and see if your answers match my answers. Well, hopefully that didn't take you more than, say, an hour, but this was a pretty hard problem, which brought up a lot of skills that you should have collected over your college algebra and pre-calculus days. If you had trouble with this, you'll have time to scroll through and see the different solutions. Notice that the domain is restricted to -4 to 4. Notice that when I was looking for the x-intercepts, I set it equal to 0 and solved. It is 0 when 2x is 0, which is when x is 0, or when what's underneath the radical is equal to 0, which occurs when x is 4 or -4. That gives us 3 x-intercepts, the origin 0, 0, which is also the y-intercept, -4, 0, and 4, 0. Moving on to the next piece, since the domain is from -4 to 4, it seems to not want to scroll too well, that means that we don't need to consider end behavior. It's not possible for x to go to infinity or negative infinity because I'm restricted between -4 and 4. There is no end behavior. There are also no vertical asymptotes or holes because there are no fractions. To find the critical points, you need to use the product rule. When you use the product rule, you should be able to apply the derivative and come up with something that looks very similar to what I have here, now ringed in pink. Be very careful when you're applying the derivative that you don't make an algebraic error. A small algebraic error can cause the whole thing to really get crazy. Once I got that, I needed to find the critical points. The critical points come from setting the first derivative equal to 0, or where the first derivative does not exist, but the function does. In this case, when I set the numerator equal to 0, I come up with 2 possible values, plus or minus 2 square roots of 2. These become 2 critical values. The next part is critical points can exist when the first derivative does not, but f does exist. We know the domain of the function is -4 to 4, including 4 and -4. However, because the derivative put the radical in the denominator, I can no longer allow 4 or -4. So though they are in the domain, they cause the first derivative to be undefined. That makes those values critical points. That gives me the critical points that are now here inside the pink box I'm drawing. In order to do the chart, I need to put these in number line order and get an approximation for the radicals. When I did that, I got -4, -2.8-ish, 2.8-ish, and 4. I let those values be the values on the vertical line for my chart. Notice that I eliminated the outside since the domain of the entire function is only from -4 to 4. I should not be looking beyond 4 or -4. When analyzing the signs, I looked at these and I discovered that it was decreasing from 4 to -2 square root of 2, and again from 2 square root of 2 to 4. The next piece is where is it increasing? which is between -2 square root of 2 and 2 square roots of 2. Now to look at the next piece. On the next piece, I need to figure out what the relative minimums are. I know there has to be one from where it goes decreasing back to increasing. That's at -2 square roots of 2. I plug that into the function, work out a lot of algebra, and I come up with a y value of -16. That gives me a relative minimum here at this value. The other extrema is going to occur when it goes from increasing to decreasing. When it goes from increasing to decreasing, then I must have a relative maximum at 2 square roots of 2. Plugging it into the original function, I get the point 2 square roots of 2, 16. This is the relative maximum. Now I need to consider concavity. In order to find concavity, I need to take the second derivative, which means take the derivative of the first derivative. Notice that because the first derivative is a quotient, this will involve the quotient rule. I started to run out of room and my work got a little jumbled, but hopefully you'll be able to follow this. It took a lot of algebra in order to simplify this problem. You may want to pause the video here until you're sure that you can follow all the steps. Notice, for example, that this part here is the numerator of this line here. It is not a part of the very first line up here. When I was done simplifying, I had a much simpler form for the second derivative, which consisted of the part down here that I will now ring in the hot pink color. Once I got that, then I could look to see where the second derivative changes sign. When it changes sign, we have an inflection point on the graph. In order for it to change sign, it has to have a 0 in between. This means that I'm looking for where the numerator is 0. I took the numerator of the second derivative out and set it equal to 0. This will occur when x is 0 from the 4x monomial factor, or when the binomial factor x squared minus 24 equals 0. Solving the second one, I get x is plus or minus the square root of 24, but that's very close to 5. These numbers are both outside my domain of -4 to 4, so I can ignore them. That means that the only place that my second derivative can be 0 or can change sign is at 0, the origin, that we found previously when we were looking for intercepts. I have reproduced the second derivative here, and I split it up into its 3 factors with another line for the second derivative. It can only change sign at 0, so I take test points to the left of -1 and to the right of 1. Plugging these into the 3 factors, I get these signs you see in the first 3 rows of the chart. By combining the 3 signs, I can get the sign of the second derivative. When it's positive, it is concave up like a cup, and when it is negative, it is concave down like a frown. Because it changes sign here from positive to negative, I know that at x equals 0, I do in fact have an inflection point. Since I already found that 0, 0 is on the graph, I don't need to plug it back into the original function, though of course I can do that. And now I'm ready to put all the information I have on the graph, and you will see the graph on the left-hand side that I hand drew to produce it. On the right-hand side, you'll see Desmos's version of the graph, which is relatively close to what I have. Notice that it is indeed concave up from -4 up to 0, where it changes to concave down until it gets to 4. Notice that it does have a relative minimum here of what would be about 2 square roots of 2, -2 square roots of 2, and -16. It also has a relative maximum here at what must be 2 square roots of 2, +16. This is the method that we will use in order to estimate the graph of the function. Be aware that these can take a tremendously long amount of time to do, and it is very easy to make a small algebra error that causes extreme problems down the road. My advice is to use Desmos to guide you and to make sure at each step that you haven't gone off track. When you're taking an exam on this, I will break these up into separate pieces so that you can be tested on each piece individually without having to do all of it at once, since that's prone to lots of algebra errors and simple mistakes. This is the end of the video for the section on 4.6, how to graph functions using the information you can glean from college algebra and calculus.